Hello, everybody, and happy Trig Day. We are finally here. I'm so excited. This is the day I wait for all year long, and I'm so excited to finally get to share this with you. So we are going to start really small, okay? This is probably the first time since back when you were pretty young and looking at Algebra 1 where you had to learn what a variable was, what a constant was, what an equation was. Those are all things we take for granted now that we just know. We are starting a completely new field of mathematics. Trigonometry is totally new. You've never learned this before. There's going to be a ton of vocabulary that is new to you, a ton of rules that are new to you. And so you need to treat this like the baby steps that you took when you were learning Algebra 1 for the first time. You don't really have a frame of reference for any of these things, and so that's where this can be a little bit challenging. So take the time, work on flashcards as always, and those sorts of things, but I'm so excited because this is my favorite part of the whole year. So we are going to start in this first section by looking at angles and radian measure. So radians are a way that we measure angles. We're probably used to working in degrees, and we have a good idea of what a degree represents, but in math, and especially in calculus, we use radians to measure angles for several different reasons, but it's a different units, sort of like meters and feet are different units, different measurement systems. Radian degrees are two different ways to measure an angle. So it's different types of units. So first we're going to kind of standardize our vocabulary about an angle. So an angle is going to be defined as two rays that have a common endpoint. You probably know that already from geometry. Now what's a little bit different in this class is those two sides are not the same. You have one side, in this case BA, which is the initial side. And so if you imagine these two sides as if they were stacked on top of each other, like here's two different rays, okay? And then this ray here is going to swing open, and it forms your angle down here, okay? So that's what happens. Your initial side is going to stay put, and the terminal side is going to rotate around the vertex to create your angle. Now, this symbol here is the Greek letter theta with a TH. So it's kind of, that's how I typically write it. It's an O with a line through the middle. Quickly, we tend to just kind of write it like cursive. And again, that is the Greek letter theta with a TH, not theta with an F. It's not cheese. So theta with a TH, that's what that angle means, or that symbol means. We always use Greek letters to represent angles in trigonometry. So you're going to see that one a lot, and we'll see some other ones as we work through. So once we know where the where the initial side and the terminal side are, then it makes sense that we could draw angles in a whole lot of different ways if we didn't agree on a standard way to draw our angles. And so that's why we've determined the standard position for angles. And so an angle is in standard position if it has a vertex at the origin and its initial side lies along the positive x-axis. So you can see these are two examples of angles in standard position. The blue is their initial side. The initial side always stays on the right side of the x-axis, and then we rotate to create our angles. Positive angles are formed by a counterclockwise rotation, and I think of it almost as we're moving upwards from the initial side, so that's how I correlate that to positive. If we're moving clockwise, we're going downwards from the initial side, and so that makes a negative angle, okay? Here is another Greek letter. This is lowercase alpha. So that's another one that we'll see frequently. I'll tell you the other ones kind of as they come up. Okay, so alpha is a positive angle. Theta, for part B, is a negative angle because of the direction that we have rotated. Okay, now we determine the location of an angle based on the quadrant where its terminal side lands. Now, something that you probably haven't had to think about a whole lot since Algebra 1 is how to name your quadrants. So the first quadrant, quadrants are named with Roman numerals. The upper right, where it's positive x, positive y, is quadrant 1, and then we move counterclockwise. Quadrant 2 is this one, quadrant 3 is this one, and quadrant 4 is this one. They're always named using Roman numerals, so you need to learn them that way. So if we look at this one here, the terminal side landed in quadrant 2. So alpha is in quadrant 2. On this one here, this is in quadrant 3 where we landed. So theta is in quadrant 3. Okay. If your angle happens to land on the axes, so not in between, but so here's my initial side, let's say. And let's say that I rotate all the way around and stop right here. So that would be a 270-degree angle. But since it landed in between quadrant 3 and quadrant 4, we call this a quadrantal angle. And we would say that it landed on the positive y, or sorry, that's not positive, that's the negative y-axis, is how we would describe its location. Okay, and again, that's called a quadrantal angle. So this is all vocabulary that you have to be aware of. These are the kinds of things that you're not necessarily going to see in review problems, but they would show up on the test. So you got to study both things. Okay, so we are used to measuring angles with degrees, and this is just a refresher for you of where the classifications for angles can come up. So an acute angle is between 0 and 90 degrees. A right angle is going to be an example of a quadrantal angle because that would land on the positive y-axis. That's a 90-degree angle. Obtuse is going to be between 90 and 180, and then a straight angle would be another example of a quadrantal angle, is 180 degrees. With degrees, we can keep going. And so you would get to 270 and then 360 if you keep going around on the axes. But once you get past 180 degrees, we don't really give them a name anymore. So acute, right, obtuse, straight, and then anything after that is just a big old angle. Okay, now radians. Radians are another way of measuring angles. So again, think of it as it's just a different type of unit, like gallons versus liters, meters versus yards. So it's just a different type of measurement system, but this is what we use pretty much in all upper level math. So the definition of a radian, and this is what our project is going to focus on tomorrow. 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of a circle. Now, that's a lot of geometry vocab that we haven't seen in a while. When you have 2 rays that create an angle like this one here, so I have one and the other, the intercepted arc is this chunk of the circle here that we trapped between the 2 sides, okay? So what we are saying, the measure of 1 radian is where the length of the radius has the same length as this intercepted arc. So if you were to imagine this curved arc kind of stretched out straight, it would have the same length as the radius. Okay? That, when you have a radius and you measure the arc that way, the angle that you're left with inside represents 1 radian. Okay? So 1 radian is much bigger than 1 degree. We know there's 360 degrees in a circle, and if you just kind of were to estimate, you can see there's going to be around 6 radians in 1 circle, close to it, okay? Here is how we determine the radian measure of an angle given the circle. So if we have an arc of length S on a circle of radius R, Okay, so if S is equal to R, then theta is equal to 1 radian. That's how we define 1 radian. But if it's not, we need to figure out, basically looking at S, how many measurements of R did we squeeze in there? So we're going to take S and we're going to divide it by the radius, and that's going to tell us how many radians we have. So let's look at a couple of examples. This is pretty easy. So number 1 says a central angle theta in a circle of radius 6 inches intercepts an arc of length 15 inches. What is the radian measure of theta? So again, theta is equal to S divided by R. Well, this is your radius, and this is your arc. So the measure of theta is going to be 15 divided by 6, which reduces down to 5/2 radians. Or you could say 2.5 radians here, either way. Okay, so that's the measure of theta in radians. Take a second to pause the video and try number 2 so you can see if you are doing that correctly. So for number 2, here's our radius, 12 feet. Here's our arc length, that's S. So theta is equal to 42 divided by 12, which is, let's see, I think we can divide them both by 3, maybe 14 times, 14 thirds radians. I think that's right. 21 over 6, 14 thirds. Okay. Now, sorry, fourths, not thirds. I can get out a calculator. Okay, so since degrees are what we are familiar with, then we want to be able to convert back and forth. And so the way we do this, if you remember in chemistry, kind of doing your dimensional analysis, you have this conversion factor. It's the same idea as like there are 3 feet in 1 yard. So 1 yard over 3 feet or vice versa. The relationship that we are going to use is the fact that pi radians is equal to 180 degrees. Okay. And what that means is that if I am looking at a circle, whoops, not that one. Hold on. That drew weird. There we go. Okay, so here's a circle. If I have my center right here, if I want my radius to be this way here, okay, my angle can go to this side, and that's going to be a 180 degree angle. But the length of this arc here is also going to be half of the circle. Well, since the circumference of a circle is 2 pi r, half of 2 pi r is just going to be pi r, but whatever the radius is doesn't really matter because the arc length is always going to be pi. And we'll talk about that in a little bit more detail. But so 180 degrees is half the circle. Pi radians is half the circle. Okay? So that's always how we want to think about that. So if I want to convert to radians, I take degrees and I multiply it by pi radians over 180 degrees. That cancels out degrees. If I want to convert the opposite way, we flip it because we want radians to cancel. So right now, if we look at number 3, we have 30 degrees and we want to convert that to radians. Well, right now I have degrees, so that means when I multiply, I need to have degrees on the bottom so that they cancel, which means then I need pi radians to be on top. So the degrees are going to cancel out. 30 over 180 is 1/6. So we end up with 1/6 pi, or pi over 6 radians. Take a moment to try B and C and check your work. These are the answers you should get. And it is worth noting, we've been writing radians on here just to kind of emphasize that that's the unit that we are in. We use radians so much that if you don't put a symbol on it, it is assumed that you are measuring in radians. If you are going to be degrees, you must put the degree symbol. Otherwise, if it's not there anyone reading it will assume that is negative 135 radians, which, as we talked about, is very much bigger than 135 degrees. So keep that in mind. Now, we can also switch the opposite direction. Okay, so I can have, for example, pi thirds radians. So now I want radians to cancel out. So I have pi over 3 radians. I need radians to be on the bottom, so it cancels. So that's my pi. And then I need degrees on the top. So this time the pi's cancel, and I'm left with 180 over 3, and that gives me 60 degrees. Now, once again, without the degree symbol, that says 60 radians. So you must include the degree symbol. So again, put it on pause, try B and C really quickly, and then you can come back and check your answer. Alrighty, here is what you should have. On B, your pi's cancel, 180 divided by 3, and then times negative 5, you get negative 300 degrees. C is a little bit weird because it doesn't have a pi on it to cancel, which is fine. You multiply, and then using your calculator, doing 180 degrees divided by pi, make sure you use the pi button, not 3.14. Your pi button on your graphing calculators is right underneath the clear button. But so when you divide that out, we get 57.3 degrees, roughly. So that gives you an idea of what 1 radian represents. It's a little less than 60 degrees, okay? Alrighty. The last thing for today is drawing angles in standard position. So we're just going to make a sketch. Now, I think this is pretty easy for you guys to figure out, knowing that a circle is 360 degrees. Degrees is a pretty easy one to figure out, but I want to spend a little time talking about radians so you can estimate where that would be. An easy way to think about this is, again, to think about where 1 pi is. So if this is our circle and we divide it into 4 quadrants, okay? I start at 0 radians here when both sides are pointing on the x-axis. Then, if I rotate all the way around, I get to 1 pi over here. And then if I rotate the rest of the way, I've gone a second distance of pi. So a whole circle in radians is 2 pi. That should help you estimate a little bit where to draw. So for example, pi fourths. Well, we need a fourth of the distance from 0 to pi. This distance here would be half, so a fourth is halfway there, so it would be somewhere like right here. So that's where we're going to draw this. So we start by drawing our axes, okay? Remember that the initial side, you always have a vertex at 0 with your initial side on the positive x-axis. So there's my initial side. And then my angle to pi fourths is going to end up right here. That's what we just looked at on the circle. And then you need to label your angle. So draw the arrow of where it's rotating with the direction that it's rotating, and then make sure you name your angle. So they told us this one was theta, so we want to label that here as theta. Okay? Now, if we think about the next one, 5 pi fourths, well, that's bigger than pi. That's 1 whole pi and 1 extra fourth. If you think of 5 fourths as 1 and a fourth. So that's 1 whole pi and a fourth of a pi. So again, here's our initial side, always the same. We're going to go a whole pi and then plus another fourth. So that's going to end up here. We've gone this whole pi plus a little bit more. And they told us that that angle was called alpha. So take a moment to think about C and D. So a couple of hints. C is going to go in the opposite direction because it's negative. D is going to go around the circle more than once because that's 2 and 1/4 pi. So think about what that would look like. I'm going to sketch mine so you can see. Okay, so for C, this is the Greek letter beta. It's drawn kind of like a B with a little tail on the bottom. that is beta. That's lowercase beta. And just so you know, this last one is kind of a swoopy looking Y, and that one is called gamma. That's lowercase gamma. You see that one in physics and chemistry quite a bit. Okay, so C, we need to go negative 3 pi fourths. So again, negative pi would have taken me all the way to here, but I only want 3 pi fourths. So if you think of it this way, here's 1 pi fourths, 2 pi fourths, 3 pi fourths. That's why we ended up there. So you're going to have to kind of start working on your fractions a little bit here. It's kind of like elementary school where you look at the wedges in a pie. It's the same kind of thing. And then this last one, I didn't draw my arrow yet for a reason. Because this one, this is where these pictures start getting kind of fun. We got to do this little loop-de-loop, because where did I go from my initial side? I started at my initial side. Here's 1 pi, aka 4 pi fourths. Here's another pi, which would be 8 pi fourths. And then I have to go 1 pi fourth more. So you get this little spiral, but you have to draw that because that is showing that you've gone around the circle more than one time. And so that's where our gamma is. Okay. So that's where we're going to stop for today. This is all the information you need to start working on your math lab assignment. You must have these notes copied down in order to participate in the project tomorrow. So I will be checking your notes at the beginning of class. See you then.